Combustion. So combustion is a chemical reaction in which a fuel will burn in oxygen to produce a common oxide, and energy is released. Could be released as heat or light or both. Now, common oxide just means whatever the substance is, the fuel is, it will be the most common oxide formed by it, like carbon dioxide, sodium oxide, in the proper chemical formula. We burn fuels because fuels give us energy. Think of a campfire for light or for cooking, right? We burn fuel if you're camping. Usually we don't burn fuel inside the house, but many of us do barbecue. So we burn propane or we burn charcoal. Charcoal is a form of carbon. Okay, so our fuels. Fuels are what we normally associate with combustion or fires, and they could be wood, branches if you're having a campfire. They could be propane if you're having a barbecue, or charcoal if you're having a barbecue. These are covalent compounds containing carbon and hydrogen. That's why they're named hydrocarbons, hydro for the hydrogen. So basically they all contain a carbon backbone. And then hydrogens are attached. So this chain of carbons, 3 carbons, is a carbon backbone, and then hydrogens are attached to them. So what I'm drawing for you now is the structural formula for propane. So many of you have propane barbecues at home. Some fuels will contain impurities that can lead to pollution, but we now have ways to get rid of most of these while we're burning the fuels. So common examples of hydrocarbons: coal, gasoline, natural gas, propane, butane, used for heat, transportation, and electricity generation. The overall formula, the general reaction, is X amount of carbons and Y amount of hydrogens. So this could represent any hydrocarbon. Plus oxygen. You will always need oxygen for combustion. And you will produce carbon dioxide from the carbon. And you will produce water. Here it's water vapor from oxygen and hydrogen. And there is energy released. Because it's released, it's written on the product side. This is not a balanced chemical equation because we don't know how many X's and Y's we have. We don't know how many carbons and oxygens we have. So, complete combustion happens when there's enough oxygen present to convert all of the carbon to carbon dioxide. So there's enough oxygen present to produce carbon dioxide. When we're using a Bunsen burner and we initially light it, the flame is yellow. And then we open the bottom so that there's an air hole, and the air is now mixing with it, and the flame gradually turns blue the more we open the bottom of the Bunsen burner. And that's because it's now mixing with oxygen from the air. Incomplete combustion happens when there's not enough oxygen. And this can occur inside a garage, if you're running a generator or a car, or inside the house. So it's a yellow sooty flame, so it's dirty, and it's not as hot. Now the problem here is that it can produce carbon and carbon monoxide. Carbon, if your furnace is producing carbon as a byproduct of incomplete combustion, then that just basically gums up all your, gums up your furnace, so your furnace won't work very well and you need to clean it. Carbon monoxide, we've all heard of that. That's the silent killer. It's odorless. It's tasteless. Oops, silent killer. Every year there's somebody who passes away because they have died of carbon monoxide poisoning. Initially, you feel sick. You've got a headache, a little bit achy. So your initial reaction is probably to go lie down and have a nap. Not a good idea. So that's why more and more houses have carbon monoxide detectors now in their house to alert them, just like fire alarms. To avoid producing carbon monoxide in your house, you should never barbecue inside your house, and you should never have a charcoal barbecue, even if it looks like it's a small and can fit on the kitchen table or the kitchen counter. You should never barbecue inside your house unless it's an electric grill. Some of you might have lawnmowers at home that are run on gasoline. So they have a choke, which is a valve that controls the amount of air going in. So sometimes as the engine's warms up, starts running, it'll sputter a bit and blow out black smoke. And that's because there's not a lot of oxygen to start. As it warms up, it will run a lot cleaner. So here's an example of a hydrocarbon that is undergoing combustion. So let's balance this. So we're assuming it's complete combustion, so we form carbon dioxide and water vapor. And we need to balance. So there's 7 carbons on the left, and there's only 1 on the right, so we need to put a 7 in front of CO2. On the left, there are 16 hydrogens. On the right, there's only 2, so we have to multiply the water by 8 to get 16. Remember, you're only multiplying by coefficients, number out front. And we're going to do oxygen last. Oxygen you do last because it's an element. So if you change the coefficient in front of it, you're only changing one element. And it's not having a ripple effect on your other entities in your equation. So on the right hand side now we have 2 times 7, so 14 oxygens, and 8 times 1, 8 oxygens. So 14 plus 8, that's 22. And because on the left we have O2, you take your number on this side, you divide by 2 for the O2, so we will need 11 molecules of oxygen. So that is balanced. There's a trick to balancing combustion of hydrocarbons. Okay, let's do butane. C4H10 plus O2 produces carbon dioxide, water, vapor, and energy. I'm just not writing in the subscripts to keep it tidier. Okay, so here we have 4 carbons, so we'll need 4 CO2s. We have 10 hydrogens, which means we will need 5 in front of water to give us 10 hydrogens. But the problem there is that will produce an odd number of oxygens on the right-hand side. So now on the right-hand side, you have 4 times 2, 8. 5 times 1 is 5, so that you've got a total of 13 oxygens on the right. You can't multiply a whole number, by 2 to balance that. So what you always have to have on the right-hand side, the products, is an even number of oxygens. And to accomplish that, if you look and you say, okay, whatever number's here for hydrogen, I need to have that and put that as a coefficient out front. If that's an odd number, if this coefficient in front of water is an odd number, go back and double your initial hydrocarbon. So 2 butanes, which means we now need 8 carbon dioxides, because 2 times 4 is 8, so that takes care of our carbons. And now we've got 2 times 10, so 20 hydrogens. So now we need to make this 20 hydrogens. So we put 10 in front, because 10 times 2 is 20. And now, if we add up our oxygens, we've got 8 times 2, 16 oxygens here. 10 times 1, 10 oxygens here. So 26, divide by 2 for the O2, and we've got 13. So if you end up, when you're balancing hydrocarbons, if you end up with an odd number of waters, go back and double your hydrocarbon reactant, and then you'll end up being able to balance with whole numbers. Now, if we have incomplete combustion, that means we have not enough oxygen to produce the common oxides. So we cannot produce carbon dioxide. So in this case, the first example here, we formed carbon monoxide and water vapor, and the energy will be less than if we had produced CO2. In the next example, we produce carbon monoxide, and some carbon dioxide, and again, the overall energy will be left. So there's a number of problems with incomplete combustion. It's not very efficient. So the energy that's stored in those carbon-carbon and carbon-hydrogen bonds are not maximized in terms of released energy. It produces soot, which is dirty and can get into places that you don't want it to get. And then it produces carbon monoxide, which we all know can kill you. Let's balance these equations. In the first one, we've got 7 carbons, so we would need 7 carbon monoxides, and we have 16 hydrogens, so we would need 8 waters. The problem with that is 7 and 8 make 15, which is an odd number for our oxygens. So we will have to double C7H16, which means we will need 14 carbon monoxides. And we have 16 times 2 hydrogens. So carbon and hydrogen is now balanced. We need to balance for oxygen. We have 14 oxygens and 16 oxygens for 30. Divide that by 2 for O2, and we need 15 oxygens. There's actually many different combinations you could do to balance the last one. I'm going to pick 2 carbons. I'm going to make carbon monoxide an even number. So I have an even number of oxygens. That's 6, so that leaves me with 1 carbon left to make 7. I need, right, that's 1, 4, 5, 6, 7. I need 8 times 2, 16 hydrogens, and that gives me with 8, 9, 10, 11, 12, 13, 14 oxygens on the right. So I need 7 oxygens on the left. And that's balancing complete and incomplete combustion for hydrocarbons. Sometimes our fuel is actually a metal. And metals will react with oxygen, or combust with oxygen, or react, depending if it's fast or slow, and you will produce a metallic oxide. So just make sure that your formula is correct. Oxygen having a charge of -2 combined with your metal in your product, and then just balance accordingly. So in this case, I would need, for sodium oxide, I'd need 2 oxygens, which means I need 4 sodiums. And then the next equation, I need 2 calcium oxides to balance oxygen, so I need 2 calciums. When you dissolve these products, these metals, metal oxides, in water, they will turn a pink color if you add phenolphthalein. So you will be able to test if your oxide is metallic by dissolving it in water and adding the indicator phenolphthalein, because if your solution turns pink, you've made a base. So metallic oxides react with water. Your metallic oxide will react with water to produce a hydroxide. Nonmetals, on the other hand, will produce a non-metallic oxide. So carbon burns with oxygen to produce carbon dioxide. Nitrogen might burn with oxygen to produce nitrogen monoxide. There's a whole bunch of different nitrogen-based oxides. This will need a 2. And it will also release some energy. When these solids, though, are dissolved in water, you will produce an acid. So if you've added phenolphthalein to your oxide in water, if you produce an acid, you will not see a color change. It will stay clear and colorless. So you would actually have to pick a different indicator to prove that it's an acid. So in this case, sulfur dioxide reacts with water to produce sulfurous acid. Please remember, for all combustion reactions, you have some substance, some fuel, plus O2. So your second reaction for a combustion reaction will always be oxygen gas.